Yeah, there you go. So if you're in my calculus 2 this morning, I don't know what's going on. My microphone's like going in and out, like I don't know why. So hopefully it's not doing that right now. Otherwise, I've got something to buy later today. Anyway, every so often I have to buy a new mic, you know. Let me begin with a word of prayer. So, dear Heavenly Father, we thank you for this day. Again, I thank you for these students. Just ask that you be with us. Help us to understand physics today. Help us to understand your creation a little bit more deeply together, Lord. In your name I pray, Lord Jesus. Amen. So I figure I'd just start here with just a couple of simple examples. This is from Lecture 8. And so you don't have to write this down. You can just follow along with me. It's in the PDF. You can look at it, right? So here's one. Suppose you've got a car and it brakes and stops from its initial speed of 50 meters per second with a friction force which is 1/10 its weight. What's the stopping distance? So here's a picture. That's my version of what the car. It looks like the one you guys own, right? And so it's initially going 50 meters per second. It ends with it stops, right? So the final velocity is 0, initial velocity 50 meters per second. And we're told that the braking force, which is due to friction, right, is minus 1/10 its weight, right? And so, you know, MA is equal to minus 1/10 mg. I divide both sides by m. And so my acceleration is minus g over 10. And I use my timeless equation because this is constant acceleration. And there you go. So, you know, whatever that number is, 50 meters squared divided by 2g over 10. Did I not calculate that in here? Oh, man. Lazy punk. Grief. Oh, no. My children have stolen my calculator again. Golly. No, it's probably just, well, it's probably just sitting in my office. Oh, well. Sorry about that. Anyway, the number is really less important than the idea here. I don't know, it's just 2,500. Let me not try to do that in my head. That's the stopping distance, all right? Now, what's going, oh, a calculator? Ooh, a TI. Thank you. I mean, beggars can't be choosers, right? Let's see here. I mean, I was raised on Texas Instruments, but I grew past it. Oh, there's a square. Multiply by 10. Divide by 2. Divide by 9.8. I get basically 1,275.5 meters. So, whoa. That's like a 1.2 kilometer stopping distance. That's not too good, is it? That's pretty bad. So, not good. Okay. Now, what's going on here in this problem? Here's the free body diagram. So, like, we're always using F equals ma, right? F is the net force is equal to the mass times acceleration. So here, I didn't even really need to talk about it. But there was a normal force and there was a force of gravity, right? Those didn't even come into play with the motion. The question, those are balanced out, right? I mean, apparently the normal force is supplying the force due to friction, yeah? And which is apparently just, you know, in this case, 1/10 of the weight. So that's the free body diagram here. It's not especially interesting. Let's move on. So again, an easier example, suppose you got a particle, it accelerates at 5 meters per second with a net force of 10 newtons applied in the x direction. What's the accelerate? What's the mass? Well, we have, you know, A is F over m, so m is F over A, and the mass apparently is 2 kilograms if that's the situation. So they don't have to be hard, right? Some of these problems can be easy. We go on here. We talked about that before. This one's a little bit more interesting. Suppose you're in an elevator, all right, which accelerates upward at 1 meter per second squared. What's the normal force on your feet? So here's a picture. My elevator, we're going, Mr. Top Hat's in there, it's going upwards at 1 meter per second squared, right? So how do we work this? Well, I'm going to write Newton's, I'm going to write Newton's second law with respect to the fixed frame, not the elevator frame, but the frame of reference where the elevator's hanging, right, and moving up and down. So mass times acceleration is the normal force plus the force of gravity. So I'm writing, this is Newton's second law applied to Mr. Top Hat, all right? What are the forces at play on him? The normal force from the floor, right, the floor pushing up on his feet, and gravity pulling him down. That's it. So we are given that the acceleration is 1 meter per second squared. J hat is just upward, right? N minus mg. So apparently the normal force has to balance this equation, and the normal force is exactly mass times g plus 1 meter per second squared, right? So, for all intents and purposes, Mr. Top Hat feels about 10% heavier than usual, right? If you can imagine the elevator, instead of accelerating at 1 meter per second, if it accelerated at an acceleration of g going upwards, then he would feel twice his weight, right? He would feel twice as heavy as usual. If, on the other hand, the elevator is accelerating downward, well, you've all experienced this, right? Not in this building, but in a building where you can experience acceleration in the elevator, right? They exist, just not here. Go to the parking garage, right? You kind of feel that sense of weightlessness when you drop, right? Because it accelerates downward, at least a little bit. But anyway, this is how we should work problems with elevators. Mass times acceleration is sum of the forces. Just make sure that you write the equation with respect to the fixed background, and you can solve these. So I hope that helps you with the homework problem, which is somewhat related to this one, yeah? Let's see here. And here's one final example, then I'll start writing stuff out. You have a squirrel with initial speed v naught, and it goes the distance x naught into a tree. Suppose the squirrel decelerates uniformly. What was the braking force applied to the squirrel from the tree? Suppose the squirrel mass is m naught. So here's a picture, squirrel before, squirrel afterwards. It took distance x naught to stop it, right? So we can do the timeless equation, vf squared equals v naught squared plus 2a delta x. In this case, the final velocity is 0. And so that means the acceleration we can solve is minus v naught squared over 2x naught. So what was the force? What's the average force? The average net force in this situation would be m0 times a, right? And I found a is this, so I plug that in. So the net force of the tree on the squirrel would be minus mv naught squared over 2x naught. And it's negative, of course, since the force is pointing that way, slowing down the squirrel, right? And some student, a number of years, was kind enough to give me a picture of this. So, well, here we have a number, 1290 meters. Man, what kind of gun do you need to shoot a squirrel 1290 meters per second? I don't know about you, but I don't want to get hit with a squirrel going over 50 meters a second, you know? And so there's the result, 5 centimeters anyway. So, all right, dumb pictures from lecture 8 aside. Let's move on with our life. Yes, sir.
Are the material properties of the tree built into the life equation?
Does the what?
Material properties of the tree built into the life equation?
The material properties of the tree are ignored. This is we're assuming uniform deceleration of the squirrel. So.
But what is that deceleration based on the hardness of the tree?
Well, here, I think it's not really a reasonable assumption because he's going into a knot, which would have kind of like a non-uniform density. I don't know. I mean, you have to make up your own backstory here, right? If you don't like the physicality of the example, replace the tree with a block of cheese. And that's a little bit more reasonable, you know. Actually, there's nothing reasonable about this discussion, but let's go on. Okay, so I have a little bit more to say about circular acceleration. Suppose you've got, oh yeah, thanks, I think I zoomed out, I need to fix it. I don't ever make you guys do the zooming. Oh, it's fine, okay, cool. Okay, so circular motion, suppose you're going around a track like this, right? Then, you've got some sort of tangential speed like this v, right? What did we learn? We learned that the centripetal acceleration, right, AC is v squared over r, right? And the other thing that I don't think was, I haven't quite clarified this yet, but I should. The formula for the tangential piece, so there's also a tangential piece of the acceleration, right, which could be like this, AT, right? So the net acceleration is the sum of these two guys, yeah? So if you want the net acceleration, I do tip to tail, so I like just move this blue vector down to here like so, right? There's my AT. It's perpendicular to AC. And the net acceleration is the vector sum of the tangential and the centripetal piece here, yeah? And so in the picture, it would look something like this, right? Here's the actual acceleration vector, right? So in calculus 3, you prove this. Acceleration is minus kappa v squared, unit vector in the n direction, plus dv dt, unit vector in the tangential direction. Now here, kappa equals curvature. And so that's actually 1 over the radius of curvature. So if you take a circle, you take a path. Let me just show you a picture like more general, like this. So the curvature, what that means is it's like if you fit a circle like this inside the curve, the curvature is simply that circle that you fit. This is the osculating circle. This distance right here, r, well, the curvature is 1 over that r. So like over here, you fit a circle inside right here, right? Well then, the curvature is still 1 over r, but, well, let's say r2, let's say r1. As you can see, the curvature is what? The curvature is smaller over here, right? And it's bigger. So the curvature, basically, the bigger the curvature is, the more curved the curve is. The smaller the osculating of circle that fits in there. And the larger the normal component to the acceleration you need to continue that motion. On the flip side of things, the tangential component is just the change in speed per time. So, for example, if you're going constant speed circular motion, there is no tangential component, and what do you get to say? Well, the acceleration is just inward all the way around, right? So for constant speed circular motion, the acceleration is just equal to v squared over r. But generally speaking, since these are perpendicular, right? What's the formula for the acceleration? It's the square root of v squared over r quantity squared plus dv dt squared. All right. So what would like the what would the equation of if we're talking about a car, right, and it's going around a flat track, yeah? So what's going on? What are the forces at play here? If I can foolishly attempt to draw it over here, I never can draw it three-dimensionally. No, let me just not even try. So if you look at it, there's the normal force going up, right? You've got mg going down, right? And you've got the, well, and here's where I get into trouble. Then you've got the force of friction. Well, that picture is not helpful to you at all. Where'd my thing go? Let me just get to the point here. Because in the vertical direction, the normal force is opposed by gravity, the normal force is equal to mg in this situation if it's a flat track, right? So for a flat track motion, you have that, ma, you have ma is equal to, well, what is it equal to? In this case, it's equal to mv squared over r. Oh man, it's still wet. And that's in the, oh goodness gracious. I don't even want to, I'm sorry guys. I'm having trouble making a decision. Let me just not write the vector thing here, just get to the point. So the mass times acceleration in this context, right, is equal to oh, phooey. Well, mv squared over r, right? So here, if I write that, what am I talking about? The what? Yeah, the centripetal force, yeah. So to be clear, so I really should put an AC here, right? Because if you go back, it's the centripetal acceleration that was matched by that. That's what we derived the other day. And I'm sorry, guys. I've got some kind of mental block here at the moment. What's that? Yeah. It has to be less than the friction force. That is true. You know, the question is, why is this happening? Well, like you said, you're right. It has to be less than the force of friction, right? But that still doesn't quite describe what's going on here, right? Because the larger point here is that the mass times the acceleration has to be equal to the friction force. I mean, that's what's keeping it in play. The normal force and the force of gravity, those cancel out, right? So when you look at just the magnitude of the acceleration, we get this. And the flip side of it, so this is equal to, this is less than or equal to mu mg for what I was just saying. And the tricky thing is, in the case that it's not constant speed, this right here is what? Well, it's the mass times the square root, you see, of v squared over r quantity squared plus dv dt squared. So there we go. Now I think I have redeemed myself here. So that's the situation. And so if you want to do if you want to find max speed for a given, you know, if you have some problem, like I think a problem in the homework I give you that dv dt is like 2 meters per second squared, right? So you have to ask yourself, if I'm saddled with, I'm speeding up going around the corner, right? If this term right here is 2 meters per second squared, and I have to square that, how do I get maximum speed here? Like what's right on the breaking point is when you have this is equal to mu mg, right? That's your max speed. So that's all. This is just like a very large hint for your homework problem, essentially, yeah? The thing that's messing with me is I'm getting tempted to try to like write down the vector background of this, and I can't quite draw the pictures because they're three-dimensional. But anyway. All right, let's go on here before I waste more of your time. I mean, I don't think this is a waste. This will help you with the problem. Let's talk about inclined plane. So, yep. There we go. There we go. Now we got an inclined plane. I really need to get a better ruler. This thing is heavy. Very bulky. So this was example 1, I suppose. So example 2. Suppose you have an inclined plane like so, right? So we talk about the angle of inclination here, theta, all right? And let's suppose that we have a box sitting up here, all right? And to start with, we'll just say that the plane is a frictionless plane, all right? Friction negligible. But what we're going to do is we're just going to see what happens here if we just let the box go. Yeah? What's the acceleration of the box? How should we understand this? Why does the box slide down the plane, by the way? Gravity. Very good. So, I mean, I think that's a totally reasonable answer. So, gravity acts on the center of mass, and it goes down like so, right? mg. Now, does the box just fall according to the mg force? No, it doesn't, right? The plane keeps it from doing that. What are the other forces involved here? The normal force, very good, which points normal to the plane, right? So normal force. Let me shorten mg here a bit, just to make it more. I mean, you don't have to draw these arrows so that they're to scale. I'm just trying to kind of sort of draw them to scale. And then what else is, well, I mean, that's it, right? In terms of forces that are on the box, that's it, right? There's the normal force pushing up, there's gravity pulling down, that's it. So what's the acceleration? I mean, it is accelerated, right? So for this kind of problem, it's useful to introduce a concept. Now your book, it might use like X and Y coordinate systems, which are tilted. I refuse to do that. I will use what I call the parallel and the perpendicular directions. All right, so like the normal is pointed in the perpendicular direction to the plane, right? The parallel is what it sounds like. So see, I can break gravity into two pieces. See, gravity can be decomposed into this piece and also this piece, right? And so how do you, let me blow that aspect of it up here. So I'm saying we can take gravity. I'll make it bigger down here like this. This is my mg vector, right? And I can decompose that vector into a piece which is parallel and another piece which is perpendicular, right? So you guys tell me, where's theta in the triangle, the vertical triangle I just wrote? It's at the bottom, that's right. So theta is right here if you look at it. And maybe you can see it better up here, right? So if this is theta, that angle's complementary to theta, which means that this is complementary to the angle complementary to theta, which makes this theta. Anyway, however you got to see it, that angle's theta. All right? And that being true, we've got what? We've got a right triangle, right? So you got mg here. And so here we've got mg sine theta. And the perpendicular one is mg cosine theta. So what's the whole story here? Well, we can look at Newton's law, right? Newton's law says that the mass times the acceleration parallel is equal to the sum of the parallel forces. If you'll allow me this language, the mass times the acceleration perpendicular, it's equal to the sum of the perpendicular forces. All right? But what else is the situation here? Well, we're on the plane, right? So what's the perpendicular acceleration? As long as it's sliding on the plane, the perpendicular acceleration is 0, right? It's not lifting off the plane, it's not going into the plane. So this has to be equal to 0, right? But what are the perpendicular forces here? We've got the normal force going upward, right? And what else do we have? Right, part of cosine, mg cosine theta going into the plane. And by the way, since the, since the perpendicular acceleration is 0, it stands to reason that the, the magnitude, well, let's just say that we could really drop the parallel and just say A there if you wanted, but I'll keep with it. A parallel, mass times A parallel is equal to what? What's this mg sine theta, right? So if I write mg sine theta here, I could do that, yeah? So what's the acceleration parallel? G sine theta, right? So we have acceleration parallel is G sine theta, and this right here tells us in this case the normal force is mg cosine theta. Does that make sense so far? Now if I write these equations, what's my convention? Is down the plane positive or is down the plane negative? You see, you can choose whether you want down the plane to be positive or negative. I've just made it positive, right? Because I've written a plus for mg sine theta. See that? Once I write this equation here, I have defined by writing that downward to be positive. Does that make sense? I mean, we're assuming that. Down the plane is positive. Okay, so this is like the simplest version of this problem. Now let's add things to it, right? Let's add friction. How does this change with if we add friction to it? Now, with friction. All right, so we draw the free body diagram. Okay, so here's the deal. You got your normal force like that. You've got gravity perpendicular to the plane. What's the perpendicular part of the gravity? We learned in the last example, mg cosine theta. Mg cosine theta is this piece. This is the perpendicular part of gravity. There's also the parallel piece of gravity to the plane, right? Mg sine theta goes like this. Right? That's everything we had in the previous problem. I just broke gravity into two pieces, the piece perpendicular to the plane and the piece parallel to the plane, okay? What other forces are at play now? Force of friction. Where does that point? Opposite the motion, opposite the potential motion, right? So, like this, yeah? Okay. So then the question is, does the box slide? What's the maximum angle that we can put the box at before it slides, yeah? You know what I'm talking about? Like, here's a box, right? You get the idea? It'd be more fun if I had something, oh, here. Right? This is going to be a fun story about how did your screen get broke on your phone today? Well, it was for physics. This phone's a few years old. It's worth it. Okay, so what's the max angle before the box slips? Yeah? Ah, right. So we know that the force due to friction is less than or equal to mu sub s times the normal force, right? And what else do we know? Here, we know that 0 is the mass times the perpendicular acceleration, right? Which is also what? N minus mg cos theta. So lo and behold, the normal force is mg cosine theta. But we also have 0 is equal to the mass times the parallel acceleration, right? Because we want it to be just before it starts sliding, right? So what's the sum of the forces in the parallel direction? You've got the force of friction. And so here, if I'm going to make down positive, then I've got mg sine theta, right? Minus what? Force of friction, which in this case, we're going to max it out. So mu Sn. Yep. So what happens? We got, apparently, mg sine theta is equal to mu sub Sn, which is what? Mu sub s mg cos theta. You're like, but you never told me the mass of the box. That's right, it doesn't matter. Right? The angle at which it slides is completely characteristic. It wouldn't matter, you know, if I had another phone that had, you know, 2 batteries on it rather than 1 and weighed twice as much, and it had the same case and everything, so the coefficient of friction between this and the laptop was the same. The angle at which they started sliding would be the same, yeah? So anyway, that's a lot of there's a lot of fine print, isn't it? But fine print's the kind of thing you expect with a phone, so it seems appropriate. Let's see here. So yeah, mg's cancel, and you got yourself a tangent theta is equal to mu sub s. So the angle of inclination, the maximum angle of inclination before this thing starts sliding, is the inverse tangent of your coefficient of friction. So for example, if your coefficient of friction was 1, which would be like really good, yeah, then 45 degrees, right? Any questions? Or? What if it starts sliding though? Then what's the situation? Well, if it was sliding, right? If we're past this point, right? If mg sine theta is greater than the maximum force of static friction available, then what happens? It slides down the plane, right? What's the acceleration in that case? If it slides, then what? And that would be the case. Mg sine theta is greater than mu sub s n. Yeah. Then we're in the kinetic. Then we become kinetic. We have to use the kinetic coefficient of friction, right? And we'd have, you know, mass times the acceleration parallel would be equal to mg sine theta minus mu sub k times the normal force. The normal force would still be mg cos theta. And so there you go. That would be what you're up against. Of course, you can divide by m, right? And you can get that if it is sliding, the acceleration would be, you know, g sine theta minus mu sub k g cos theta. And we could put numbers in, but this is the idea. Yeah. Any questions? What if we push on the box? Then what happens? If I go back to my example, well, let me erase the evidence of the of this. By the way, you don't have to know that curvature stuff I was talking about. I'm just mentioning that because if you're, when you take Calculus 3, you should see a little bit of that. And anyway, that's really a comment from Calculus 3, not so much for here. Anyway, okay, so what if we're pushing on the box? Then what happens? The question is, how are you pushing on the box, right? So just to keep things relatively simple, let me suppose we're pushing horizontally on the box in the sense of horizontally. Well, let me just picture it. Suppose that you're pushing on the box like this. Suppose you're pushing on the box horizontally up the plane like that. All right? Do you guys want this with or without friction? With friction? All right. Example 4. All right. Then the question can be, what angle is the max angle we can go with before it starts slipping? Right? We can ask that question again. For a given F naught, which is in this direction on the box, when does the box necessarily slide down the plane? This is the situation. So what we want to do is I'll just come over here and draw the box again and just kind of draw the different actually, instead of drawing the box, let me just replace the box with a dot. All right, let me replace the dot with a box. And we replace the box with a dot because it's easier to think about that graphically. What's going on here? Well, you've got, on the one hand, you've got the force going like this, right? F0. What else is going on? You've got a normal force, still perpendicular to the plane. That's how normal forces work. That was perpendicular to the surface. And then what? Well, gravity. Yeah? So I'll draw gravity as if I'm going to draw gravity like this. All right? But both the gravity and the F0, what do we want to do with those? See, because we want to work in the perpendicular parallel sense, right? So we already talked about how to break gravity into the parallel and the perpendicular pieces, right? We know that, right? We know how to do that. Let's do that again. And so we know that if we look at this part of gravity and then that part of gravity, we can do that, right? This is what? We've got mg sine theta here, mg cosine theta over there, right? But what's the story for F0? How can I break that vector into its parallel and perpendicular piece? Right? I want to find this vector here and this vector there. Right? Those will be the components. The part of F0 that's parallel, the part of F0 that's perpendicular. So what's the situation? Well, see, it's different than the gravity, yeah? Gravity, the angle theta appears here in that triangle, right? But for the F0, the geometry here puts theta right here, right? So the part that's parallel for F0 is actually F0 cosine theta, whereas the part which is perpendicular is F0 sine theta. And of course, it's opposite in direction to the normal force, yeah? Where's the force of friction? Like it's parallel to the plane. Is it down the plane? Is it up the plane? I'm not sure right offhand, right? Because if F0 is too big, what happens? It goes up the plane, right? So we want to think, because of the way I phrased the question, I think we want to think about F0 being small enough that it's going to have an inclination to fall down the plane, right? So if that's the case, then the force of friction goes what direction then? Up the plane, right? It tries to keep gravity from pulling the force down. So anyway, my point is the force of friction could either go up the plane or down the plane depending on how the other parallel forces balance out or don't. In short, I'm regretting that with friction because it's making my picture super cluttered. But since I did, where does friction go? Here, I'll use this hideous Carolina blue. Like this, right? But again, I'm a little bit apprehensive about that. All right, so what do we got? Mass times the perpendicular acceleration is 0, and it's what? You got yourself the normal force up, then you got your minus mg cosine theta down, and then what else? What's the other force which is going down in the perpendicular downward direction? There's one other thing, right? This piece up here, right? So minus f0 sine theta. So what's this say? This says that the normal force in this problem is not what? It's equal to what? It's equal to mg cosine theta plus f0 sine theta. So there you go. The normal force is more interesting in this one, right? That if you're pushing on the box, you're messing with the normal force as well, right? Okay, how about the parallel? Mass times a parallel. Well, since I made downward positive, and I'll stick with that since I was before and I don't want to confuse you guys, we've got mg sine theta. Anything else going down? No, so minus f not cosine theta, right? Listen, it's not so, it doesn't really matter which is down and which is up. What matters is that when you write down Newton's equation, you understand that if it goes in one direction for one and the other direction for the other, they got to have plus minus difference in the equation, right? You can't add things that are going in opposite directions, right? That's the more critical thing. It's certainly not written in stone that downward is the positive direction. So minus f naught cosine theta, then what else? Anything else? Oh, friction, right? So minus mu times the normal force, right? And if we want this to just balance out, right? I just put it equal to mu n, right? That's the max friction. This is the most available when you put it mu n there, right? So, I mean mu sub s n if you like. Anyway, so we're going to say that's equal to 0 right at the point before it starts sliding. Yep. And then you can try to solve that, you know? And I don't know. I mean, I can try. So what was, you got mg sine theta minus f0 cosine theta equals to mu sub s times n, but n was mg cos theta plus f0 sine theta. And I guess I can, let's factor sine theta out, yeah? So we've got sine theta times mg minus mu sub s f0, right, is equal to cosine theta times mg mu sub s plus f0. And then I can solve for tangent theta equals to mg mu s plus f0 divided by mg minus mu sub s f0. I feel like how did I get that mu sub s on? I feel like that's a typo. Oh, no, it's there. It's there. It happened. Oh, I flipped it. Sorry. My bad. That was supposed to be mg minus mu sub s f0 divided by, can't do math. Oh, man. Hold on a second. It's just algebra at this point, right? You can solve for tangent theta, yeah? Sorry, I think I'm working too low. You guys can't see that down there, can you? So if we solve this, we get tangent theta so sine over cosine's tangent, right? That's going to give me mg mu s plus f0 divided by mg minus mu sub s f0. See, now the mass matters, right? And you can take the inverse tangent of that. Yeah. This all supposes what? This is only valid if what condition is met. You need what? So we need that mg cosine theta, right, is greater than f0 sine theta. Otherwise, what happens? Otherwise, the natural inclination is for the box to go up the plane. It's being pushed up the plane by f0, right? In which case, our analysis is no longer correct because the force of friction doesn't go up the plane, right? It would go down the plane opposite the motion. So if that condition is not met, then we have to flip this minus here to a plus, and it's a little bit different. All right. Should we work an easier problem, maybe? What do you think? That'd be good? Let's work an easier problem. Suppose you got a box. All right, and you push on the box with a force like this. All right? And let's suppose that the angle of that force is what? Let's describe it this way. This angle here is 30 degrees. All right, you guys, everybody with me? My question is simply this. Assuming that it's frictionless, all right, assuming you're on a frictionless plane, what's the acceleration of the box? Can you figure it out? What do you want to do? Oh, by the way, for shame, I should have thought about limiting cases in all of these examples. It's always a good idea to think about limiting cases. I'll do it maybe next class. But so here, we just need to think about it. We've got mg goes down, right? And you've got this f0 like that. So if you break that down, there's two pieces, right? You got this piece, and you got that piece. Since this angle here is 30, and f0 is the length of that vector, this gives us f0 cosine 30 and f0 sine 30. In other words, if you look at the mass times the perpendicular acceleration, you've got yourself a minus mg minus f0 sine 30 degrees plus the normal force. If you look at the mass times the parallel acceleration, like I wrote there, all that you got is f0 cosine 30 degrees. So what's the acceleration? The acceleration is simply f0 cosine 30 degrees divided by the mass, whatever that is. So if I put in some numbers here, if I say f0 is, 100 newtons, and if I say that the mass is equal to, say, 25 kilograms, yeah, then what do you got? 100 newtons times 0.866, roughly speaking, divided by 25 kilograms. What's a newton? A newton is a kilogram meter per second squared, right? So those cancel and leave you what? 4 times cosine 30, whatever that works out to. 3.464, well, thank you. So 3.464 approximately meters per second squared. So, listen, the key idea here is we need to, each one of these problems, your goal is to identify all the forces acting on the problem, right? Acting on the mass in question. And then you pick a good system of coordinates to break it into two directions if it's a two-dimensional problem, right? For inclined plane problems, looking at the parallel and perpendicular direction, that's the way to go. And for these kind of problems, typically vertical and horizontal is the way to go, right? And then there are three-dimensional problems. What do you do with three-dimensional problems? Did I hear cry? No, the answer is use vectors. Like, accept your fate, use vectors.